Hello, welcome to the next section, Logistic Regression. This section begins by analysing linear classification problems, with particular focus on logistic regression, its implementation, and stochastic gradient descent approaches. Moving ahead, we'll be finding optimal hyperparameters, and then learn about classification metrics and ROC curves. Now we move on to the first video of this section that deals with logistic regression. In this video, we're going to take a look at linear classification problems, with particular focus on logistic regression. Finally, we'll implement it. Let's consider a generic linear classification problem with two classes. This is one such example. Our goal is to find an optimal hyperplane which separates the two classes. In multi-class problems, the strategy one versus all is normally adopted, so the discussion can be focused only on binary classifications. Suppose we have this dataset. This dataset is associated with given target set. We can now define a weight vector made of m continuous components. We can also define the quantity z. If x is a variable, z is the value determined by the hyperplane equation. Therefore, if the set of coefficients w that has been determined is correct, it happens that. Now we must find a way to optimize w in order to reduce the classification error. If such a combination exists with a certain error threshold, we say that our problem is linearly separable. On the other hand, when it's impossible to find a linear classifier, the problem is called non-linearly separable. A very simple but famous example is given by the logical operator XOR. As you can see, any line will always include a wrong sample. Hence, in order to solve this problem, it's necessary to involve non-linear techniques. However, in many real-life cases, we use linear techniques, which are often simpler and faster. For linear problems too, accepting a tolerable misclassification error. Let's now look at logistic regression. Even if called regression, this is a classification method which is based on the probability for a sample to belong to a class. As our probabilities must be continuous in R and bounded between 0 and 1, it's necessary to introduce a threshold function to filter the term z. The name logistic comes from the decision to use sigmoid or logistic function. A partial plot of this function is shown in the figure. As you can see, the function intersects x equals 0 in the ordinate 0.5 and y less than 0.5 for x less than 0 and y greater than 0.5 for x greater than 0. Moreover, its domain is R, and it has two asymptotes at 0 and 1. So we can define the probability for a sample to belong to a class. From now on, we'll call them 0 and 1 as. At this point, finding the optimal parameters is equivalent to maximizing the log likelihood given the output class. Therefore, the optimization problem can be expressed using the indicator notation as the minimization of the loss function. If y equals 0, the first term becomes null, and the second one becomes log 1 minus x, which is the log probability of the class 0. On the other hand, if y equals 1, the second term is 0, and the first one represents the log probability of x. In this way, both cases are embedded in a single expression. In terms of information theory, it means minimizing the cross-entropy between a target distribution and an approximated one. In particular, if log 2 is adopted, the functional expresses the number of extra bits requested to encode the original distribution with the predicted one. It's obvious that when j of w equals 0, the two distributions are equal. Therefore, minimizing the cross-entropy is an elegant way to optimize the prediction error when the target distributions are categorical. Scikit-learn implements the logistic regression class, which can solve this problem using optimized algorithms. Let's consider a toy dataset made up of 500 samples. So we first import its required things and add this code. The next set of code is for showing the plot. Next, we create the dataset and show it. Let's run it. It gives us an error. Rectifying the error, we get this plot. The dots belong to the class 0, while the triangles belong to the class 1. In order to immediately test the accuracy of our classification, it's useful to split the dataset into training and test sets. So let's do it. Now we can train the model using the default parameters. So we'll train it using logistic regression. We next check the score. It's also possible to check the quality through a cross-validation, so check it. Running this code gives the result. The classification task has been successful without any further action, and it's also possible to check the resulting hyperplane parameters. We do it using the LR-intercept function and LR-coefficient function. Let's now look at this hyperplane line. From the result, it's possible to see how the classification works and what samples are misclassified. Considering the local density of the two blocks, it's easy to see that the misclassifications happen for outliers, and some for borderline samples. The latter can be controlled by adjusting the hyperparameters, even if a trade-off is often necessary. That's all for now.